This is the 19th lecture of this course. Recall from the last lecture that where we were discussing about affine subspaces for a vector space V plus dot or for a vector space over F. A subset is said to be an affine subspace, a subset S is said to be an affine subspace if for any 2 points lying on that for any 2 points lying on the subset, the line joining those 2 points will lie entirely on the subset, and this is what we call by an affine subspace. So, an affine subspace may not be a subspace. So, you can regard an affine subspace as a generalization of the notion of a line, and then towards the end we prove that any affine subspace is necessarily of this form. So, thus this is the collection of all affine subspace, the collection of all affine subspaces, well not all. So, yeah, so let me not all. So, an affine subspace is necessarily of this form where W is a genuine subspace of V, and of course, these are for any translate of any subspace of V is also an affine subspace. Thus, so this actually thus we have the complete description of all affine subspaces, and towards the end of the last lecture we proved this. So, given an affine subspace, that means it is of this form. Since F is an affine subspace, then the dimension of W is said to be the dimension of the affine subspace. So, earlier the notion of dimension was confined to vector spaces and hence its subspaces. Now, I am extending the dimension very naturally, the notion of dimension to affine subspaces. Therefore, so for an affine subspace, the dimension of W is said to be the dimension of that affine subspace. V plus W. So, yeah. So, if the dimension of an affine subspace is just 1 less than that of dimension of V, then we call such affine subspaces as hypersurfaces. Yeah, hypersurfaces. Oh, sorry, hyperplanes. Sorry, we call them as hyperplanes. Therefore, when dimension V is 2, a hyperplane is a line, and when dimension is 3, a hyperplane is a genuine plane. Again, let me remind you that how to visualize an affine subspace. So, in dimension 2, affine subspaces are the proper affine subspaces are lines, okay, any line, and when dimension is 3, a proper affine subspace are a proper affine subspace is a plane in our usual sense that you can visualize. So, in dimension 3, suppose this is what my plane is. So, this is the plane passing through origin, and you have a vector V. So, it will be basically a parallel translate of this plane to this parallel translate of this plane by the amount V. Okay. So, yeah. So, now what we are going to do is we start with affine subspace, we start with a subspace W and consider all its translates. So, they are of this form. Okay. So, geometrically, let us say if you stick to V equal to R3, then starting with a plane passing through origin, we consider all its translates, okay, or in 2 dimension in R2 usual 2 dimensional plane, we start with a line and then look at all its translates, okay. if we look at these two pictures, we saw something very common, that is in here the or if you consider any two such lines, since the lines are parallel. So, if you take any two distinct such lines, either they will intersect or they will intersect or they will be totally disjoint, because that is what parallelism gives us. And then in fact, we prove that in arbitrary vector space of dimension 2 parallelism is an equivalence relation. Okay. Similar, so that we prove for that we have seen for dimension 2. So, and also yeah, and you see now if we come to dimension 3, then the same phenomenon goes that any two such parallel planes, either they will intersect, either they will coincide, or they will not intersect each other, and any point, and if you pick up any point in the V in the space R3, then the plane V plus V, if I say this plane is W, then V plus W is in the collection of these planes which so V plus W is in the collection of these planes which contains, so it is the plane in that collection which contains the vector V. So, what we have is, like we have a collection of so starting with a plane, we consider all its translates. This gives us that a collection of subsets of let us say in case of R3 or R2. So, any point will belong to one and only one member or only one subset from this collection, and if I take any two members from this subspace, any two different members from this collection, then they will not intersect each other. Okay. So, said theoretically, this is what we call that it forms a partition. So, when I say a set of collection of subsets of a set X forms a partition, that means every point in X belongs to one and only one member of that collection. Okay. So, this is what we have observed for R2 and R3. Hence, it is natural to ask that question in the general setup, that is, if V is a vector space and W is a subspace. So, here we are not assuming V is finite dimensional. So, V is any vector space, W is any subspace. So, we ask the question whether this collection forms a partition or not. That is actually very easy to see. So, if you remember in your set theory class, you proved that partitions or equivalence relations are interchangeable in the sense that they are equivalent. So, if I can prove that there is equivalence relation for which the equivalence classes are precisely these subsets of the form V plus W, where V runs over all elements in V, then we will be done, right, and that is very easy to see. So, if two elements V1 and V2 are in V, then V1 will be equivalent to V2 if V1 minus V2 lie in W. Okay. If V1 minus V2 lie this vector lies in W, you can easily check, it is an equivalence relation. That is very trivial exercise. For example, V1, if V1 minus V1 is 0, it will lie in the subspace W, so it is reflexive. So, if V1 minus V2 lies in W, V2 minus V1 also lies in W, hence it is symmetric. And if V1 minus V2 lies in W and V2 minus V3 lies in W, then if you add them, it will be V1 minus V3 which will lie in W. So, therefore, V1 will be equivalent to V3. So, that shows this relation is equivalence. This is an equivalence relation. This is an equivalence relation, and then starting with a vector V, what are in its equivalence collection. So, if a vector V prime is equivalent to V, that means V minus V prime has to be in W, therefore, V has to be of the form V prime plus something W. So, it shows that the equivalence class of V prime is actually a subset of V plus W, right. If V prime lies here, V equals to V prime plus some elements from W. So, this is of this form, and on the other hand, if you take any vector of this form, then subtracting V with that, it entirely lies inside W. So, therefore, anything here that also lies here. Okay. So, therefore, these collections happen to be the same. So, thus what we have proved is, so this forms a partition, in particular two such affine. So, given a, so if we fix a subspace W, so two of its translates, they so for then for any V and V prime in V, so either, so exactly one of the following is going to happen. So, either the intersection is empty or they are equal, that is V minus V prime equals to W. So, I would say exactly one holds. One holds. Okay. Exactly one holds. So, this is what we have thus proved. So, we in algebra we have so far we have called these as the affine subspaces, and that and the notion of an affine subspace, the way we define that has been motivated from geometry, right. It talks about the lines, okay. But in algebra we have a very generic terminology for objects like this, okay. We call it a coset. So, in the case of vector spaces, the cosets are nothing but the affine subspaces that we have already, which we have already talked about. Is just another name, but the nomenclature coset is a very generic nomenclature which is there in every branch of algebra. It is a very general nomenclature. So, coset, by a coset I mean a coset, let us say the coset of W by V. So, by that we mean this affine subspace. Okay. So, in this terminology what we have established is, given a subspace W, it is all cosets, the collection of its all cosets that forms a partition of the entire vector space V. Okay. Remember, in that collection only one member is, namely the W is a subspace, rest of them cannot be subspaces, because already we have proved an affine subspace cannot be a subspace unless it contains 0, and that is a necessary and sufficient condition. So, yeah, so we have in this collection. So, now we also have a notation for the collection of all cosets of W in V. So, we denote this by V mod W. V mod W is nothing but the collection of all cosets of W in V. So, abstractly speaking or algebraically speaking, a coset is just an object like this, and a set of all, and then we consider the set of all cosets. So, this description is rather somewhat abstract, but somewhat abstract, and very soon we will be putting a vector space structure on this cosets. Then so then it will make V mod W vector space over the same field F. As I have already mentioned that this well, the point that I want to make is the following, that without getting into any geometry, we can define a coset purely in purely algebraically like this, and then you can prove that it forms a partition but that we could have done that easily, there is no harm in that, but as we see that the definition is I mean, if we would have taken that approach, then the definition would be somewhat more abstract and non-intuitive. One may not have any feelings, may not have any realization of that coset, of what a coset is, and which is somewhat not desirable at the beginning. Hence, as we said that in the last lecture, I mentioned that we would rather take a geometric approach. So, we first arrive at these objects somewhat from a geometric perspective. So, throughout geometry has guided what these objects are, and then from that we from now we will entirely move on the algebraic aspects of that. So, henceforth we will deal with them purely algebraically, but as I said, we arrive at these in a with a geometric perspective. So, these objects for us, they are geometrically we will realize these objects are as the planes or lines. Geometrically we realize them as the planes or lines, okay. And these we can regard them as abstraction or generalizations of our notions of lines and planes. Yeah. So, with the geometric perspective, we arrive at something which can be described entirely algebraically, okay. So, from now onwards, as I said, I will treat the quotients, cosets and their collection, namely the quotient, completely algebraically. Okay, let us see. So, as I said that we can make it a vector space over F. So, for that again let us how to define operations on V mod W, which makes it a vector space over F. So, let us again gather our motivations from geometry. So, if you remember, so if suppose my subspace is the subspace of the form x comma 0. So, let us consider it as R2, okay. Then we suppose we take a point, any point 0 comma c. So, what is 0 comma c plus w? So, this is x comma 0. When you add 0 comma c, it will be simply this line y equal to c. So, suppose my V is my R2. So, suppose I have two such cosets, namely here we two such horizontal lines, namely one is y equal to c and then maybe another one is y equal to d. So, it is somewhere lying here or it is somewhere lying there, okay. And suppose we want to define an addition of these two lines. We want to define the addition of these two lines. So, what should be the natural choice? We we want to define the addition of these two lines, and the very natural choice is, so this if this is my line L1 and this is my line L2. So, L1 plus L2, the plus that I am going to define, it should be another line which is obtained by adding this C and D. So, it is nothing but the line y equal to is basically nothing but the line y equal to C plus D, okay. This is very that is what turns out to be the most natural choice. So, if we define like this, then it is very easy to see that the collection of all such lines with respect to the similarly we should define, if we want to suppose this is my line L, then for any constant alpha times L must be the line y equal to alpha c, okay. So, given a line y equal to c, if we want to multiply it with alpha, what should be the natural choice? The natural choice is alpha times c. So, yeah, if I just use a different notation for the time being. So, with respect to this plus and this dot, you see the collection of all vertical lines that forms a vector space, right, because it is very easy to see. So, what will be 0? So, the line y equal to 0, if we call them L0, and a general line y equal to c, if we call it LC, then you see that LC plus this L0 is nothing but LC. And in general, and if you take any other properties of the vector space, since ultimately the what is happening, we are adding either two real numbers or to either we are adding to real numbers or multiplying to real numbers. So, from the vector space properties of R, we can easily see that all the vector space properties are being satisfied for the set of all lines together with this plus and this dot, okay, because ultimately things are happening at the level of real numbers, okay. So, thus the collection of all lines with respect to these two additions it forms a vector space for us, okay. So, with this as so we it is very natural to ask whether this can be making the set of all cosets or set of all cosets of this subspace a group a vector space with respect to by defining to an addition and multiplication, whether this is very special to this subspace or this can be done if I take any other line as well. So, instead of taking this x axis, if we take any other oblique line, so the question is can or any line maybe this y axis. So, the very natural question is whether even there too we can have a similar thing, that is whether we can define addition and scalar multiplication to make it a vector space, or more generally the same question we ask that given a vector space V and any subspace of that, if we consider the collection of all cosets, whether we can make it a vector space over F with by defining some addition or multiplication. I repeat, what I am doing is, so we have observed something for this very concrete example, and we want to, and it is very natural to ask if we replace instead of this subspace, if we take another subspace, whether the similar thing goes or not, or more generally for any vector space and any subspace. We will see that indeed we can do. So, for that we have to just observe what have we done. So, we have LC is nothing but 0 comma c plus w, writing in the coset notation. So, remember, as I said, all the vertical lines are the cosets of this space, and then with that I am adding 0 comma d plus w. While doing that, how did I define it? Turns out to be, so this writing there, I mean writing these lines with the coset notation, this is what we see. This is, so therefore, we see that when we are adding two cosets, the addition of cosets is actually being performed by the addition of these two vectors and then taking its cosets. Similarly for scalar multiplication. So, this motivates us to consider this motivates us to consider whether we can perform the same in the general setup of a vector space. So, what we would like is, suppose I have suppose I have a vector space V and a subspace W, and this is my V mod W. So, then V plus W, and then if I have, so for every V1 and V2 and V, whether this is whether we can define it like this or not, whether we can define it like this or not. Okay. So, the similar thing we are going to ask for scalar multiplication. So, at a first glance it looks that since we are allowed to add two vectors, so then what is the problem with this definition, because we are in a vector space, so we are allowed to add two vectors. The problem lies in a different manner, namely the choice of V1 and V2. So, let me explain that, let me put that in this way, that given a coset, there could be multiple V's such that, so if I say consider a coset, let us say S, then there are many choices, there are many V's such that the coset becomes such that the coset S is S V plus W. Why so? So, let me again explain. So, if you remember that V plus W is equal to V1 plus W if and only if V prime equals to V plus some W for some W in W, for some little w in capital W. Okay. So, therefore, if I have a if S is V plus W, then for any small w in capital W, S will also becomes V plus W plus capital W. So, basically what are we doing? So, remember these are all equivalence classes actually under certain equivalence relation. Okay. So, even in the equivalence relation, even when we are dealing with equivalence relation and its corresponding equivalence class, so if C is an equivalence class, then it is the class of any x lying inside C. So, whenever we are dealing with equivalence class and a member lying in that class, we call it a representative. So, if my C is an equivalence class, so by definition equivalence class is non-empty. So, if C is an equivalence class, then any x lying inside that, for any x lying inside that class, C can be said as the class of x. So, therefore, there could be plenty of such x, for example, class of x is C. So, all these are the representatives of the class. Okay. So, similarly, given a cosets, it can have many representatives, and in fact, we know the description of all representatives, like, right. So, if we start with any representative, then all the other representatives are of this form. That is what we have, all the other representatives are of this form. That is what we have seen. So, now the way we have defined addition, you see that addition has been defined using the representatives, right. So, we are supposed to add two cosets. So, try to understand the problem in this way. Suppose S1 is a coset, S2 is a coset. So, we choose a representative of the coset, let us say V1 plus W, and for S2 we choose another representative from the coset. Okay. Then we, using this mechanism, we arrived at V1 plus V2 plus W. But the choice of this representative is not unique. So, another way to put that in is the following, that suppose I ask 5 of you to add the two cosets S1 and S2, and suppose yes, I ask 5 of you to add the two cosets, and I insist that you have to work independently, there should not be any communication among yourselves. Then I am pretty sure that 5 people will come up with 5 different choices of V1 and V2, and therefore possibly arrive at 5 different answers, V1 plus V2 plus W. So, I mean, looking at that, apparently it seems that in this way, given two cosets S1 S2, for the same cosets S1 and S2, there could be multiple answers. But if indeed we arrive at different such objects for different choices of V1 and V2, then certainly this cannot be, this plus cannot be a binary operation on V mod W, right. So, in order to make this well defined, in order to make this sensible mathematically, we have to ensure that this definition, I mean though it is defined to make it look very naturally, though this is defined using the representatives, but actually it does not matter what representatives you choose. So, what we have to prove here is the following, that suppose this coset is also, suppose this coset is also V1 prime plus W, and this coset, and we have for another representative this coset, I mean suppose we take another representative V1 prime from here and V2 prime for here, so that this coset is also V1 plus W and that coset is also V2 plus W, then the ultimate result V1 plus V2 plus W, then the ultimate result by applying plus and V1 prime plus V2 prime plus W, these two are same. Okay. If for any such choice V1 and V1 prime, V2 and V2 prime, we can prove these two are same, then actually then actually we are relieved, because then we don't have any danger that this then don't have any danger that this will fail to be an addition on V1 W. So, checking that is very easy. We have, if we want to show that this is equals to this, so what we have to do is, if we recall that some V1 let us say x plus W equal to y plus W, if and only if x minus y lies in W. So, you just consider V1 plus V2 minus V1 prime plus V2 prime, and now you have the liberty to group the terms properly, since V1 prime V1 plus W equal to V1 prime plus W. So, this will lie in W and that will lie in W, since W is a subspace, it will lie in W. So, now we see that, as I said, though this definition, the way it is defined, though this definition is defined using the representatives, namely if I am given two cosets S1 and S2, what I am doing is I am taking a representative of S1, so that S1, because ultimately you have to remember that you want to add two cosets and you want to get another coset out of that. So, suppose I am giving you two cosets S1 and S2, what you are doing is you are choosing a representative V1 from S1 and V2 from S2, then you add V1 and V2 and consider the corresponding coset of W by V1 plus V2. Okay. So, this rule tells you to how to add. So, this is the rule. So, according to this rule you are so starting with two cosets S1 and S2, you are getting another coset. Okay. This is following this rule, and this well definedness that indeed verifies that while performing the addition according to this rule. So, the choice of the representatives that you make, that choice actually the choices actually do not matter. Okay. So, I should go ahead now. Similarly, what should be the scalar multiplication? So, we should define, given a coset, let us say by choosing a representative from that coset, by choosing a representative B from that coset. So, the coset becomes V plus W, and for a real number alpha, not for a scalar alpha. So, it is very natural to define alpha V plus W. Again the same question can be asked whether this rule also depends on the choice of the representative. That is very easy to see. If V plus W equal to V1 plus W, therefore V minus V1 lies in W, W is a subspace. So, for that this alpha times V minus W lies in alpha times V minus W is alpha V minus alpha, alpha times V minus V1 is alpha V minus alpha V1, therefore alpha V plus W is same as alpha V1 plus W. Okay. So, exactly in the similar way we show that this also defines a scalar multiplication on the set V1 W. I repeat, my job is to given a coset W and a scalar alpha, I want to produce another coset. So, how do I do that? from that coset, I choose a representative V, let us say V, so that the coset becomes V plus W, then I multiply alpha, multiply V by alpha and consider the coset of W by alpha V. And now our verification convinces us that the V we have started with, the representative of the coset, that choice is material. Okay. So, thus we have V plus W together with two operations plus and dot. So, this is the addition, this is scalar multiplication. Okay. Now, we want to, now it is very natural to ask that yeah, it is very natural to ask whether with these two operations V mod W will be a vector space over F or not. Okay. So, actually that is a very easy task, because ultimately, I mean, once we add, ultimately the addition is happening at the level of the vectors in V, and there we have associativity and all other properties. So, I mean, if, so with this observation, it is very natural to expect that these two operations will work, in the sense that these two operations will make V mod W a vector space. So, I leave that verification of the properties to you. I will just show you one of them, namely the associativity, just to convince you what I have said of 1 or 2 minutes back, that ultimately the operations are happening though we are adding or multiplying coset by a real number, though we are adding two cosets or multiplying a coset by a scalar. Actually the thing is going on at the level of vectors. So, let me just show you. Suppose V plus W plus V prime plus W and then V double prime plus W, we have three cosets. As I said, I can start with any representative of my own choice. I can start with saying that let these be my cosets, because if we change the representatives, or if you want to change the representative for the same coset, I know that you will also arrive at the same place. So, you can start with saying that let these be my cosets, and then what is this? This becomes V plus V prime plus W, and with that I am adding V double prime plus W. So, ultimately it will be V plus V prime plus V double prime, entire thing plus W. Similarly, when we add them, we will get V prime plus V double prime plus W, and then like so we use associativity here, V plus V prime plus V double prime plus W, that shows us this is same as V plus W plus V prime plus V double prime plus W, and then this will be further broken as plus. So, it shows this plus is associative. So, you may raise an objection that I should have put plus circle here. Indeed, I should have put, because this is the notation I have used, but you see we always try to simplify the notations. So, therefore, often what we could do is we have used the notations and use the same symbol to stand for many candidates, with the convention that we will understand which one we are considering from the context where we on the context. Yeah. So, we will understand which we are talking about from the context itself. So, from now onwards I will not use plus circle or plus dot, I will simply write plus and dot, and from the context I will understand that this plus is plus in V, whereas this plus is plus in V mod W. Okay. So, thus we have arrived at the fact that V mod W is a vector space over F, and what are the operations? The operations are, for any two cosets, we first choose the representatives, then add the representatives and look at its coset. Similarly, for the scalar multiplication. So, this is you see this is nothing but so what you have initially observed for this very particular example, that is so the same holds in the generality of any vector space and any subspace. So, what we have observed there, it is nothing very much exceptional. Okay. So, V mod W is a vector space. So, now whenever we have a vector space, so remember one thing, that V mod W is not a subspace of V, because the elements of V mod W are the cosets. Okay, I mean these are not, whereas W is a member in V mod W, because why? Because what is the, so if you take V equal to 0, then what is this 0 plus W, which is 0. So, W is a member in V mod W, and in fact W is the identity element, the 0 vector in the vector space V mod W, because any V plus W plus 0 plus W will be V plus W, which shows this identity element. Okay, so V mod W is a subspace, is a vector space over F. So, whenever you have a vector space, it is very natural to ask for the same questions that we have discussed earlier. So, for example, one very natural question is whether this is finite dimensional or not, given whether it is finite dimensional or not. So, yeah, so let us deal with the question. So, in general we cannot say it is finite dimensional, right. In general we can't say it is finite dimensional. What are certain examples? The examples are very simple, that you start with let us say an infinite dimensional subspace, let us say F T, and let your W be the constant polynomials, C such that C in F, the constant polynomials. Then you see that a typical coset will look like as follows. For example, if I just consider let us say R in case, so a typical coset will look like n t to the power n plus 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 a1 t plus this coset, okay. So, plus this coset, and suppose I am given finitely many such cosets, then using them, so finitely many such cosets of this form, then that finite set cannot generate this whole vector space, because for finitely many such cosets I have representatives, and each of these representatives since they are polynomial, I have only finite such representatives, they have a maximum degree. So, I cannot, so by taking linear combinations of those cosets, I can produce a coset whose representative I cannot produce a coset which has a representative which has a representative and equivalently which has all its representatives of degree higher than the maximum of the degrees of this degrees of the representatives in that collection. So, what I mean is, suppose I have P1 plus P1 t plus W, Pn t plus W, and assume that this is a degree d1, this is a degree dn. So, we can arrange these elements in such a way that dn is the maximum. So, once I consider any linear combination of them, then a typical linear combination will be the coset of a linear combination of P1 P2 Pn, and for the linear combination of P1 P2 Pn its degree cannot exceed dn. So, therefore, if I now consider this coset to the power dn plus 1 plus W, then this cannot be written as the linear combination of this. So, in general the V mod W we cannot regard it as a finite dimensional vector space. However, one thing you must have observed in this example, that I have started with a V which is itself not finitely generated. So, if you remember how we proved that V is not finitely generated, the technique was the same for any given collection of exactly the same technique I used for any finite collection of polynomials, it has a maximum degree. So, therefore, as a linear combination I cannot obtain the polynomials with higher degrees. Okay. So, the same technique also goes here as well. So, the upshot is I could have arrived at this example where the quotient space. So, from now onwards I will call V mod W the quotient space. The quotient space is not finite dimensional because I started with a infinite dimensional vector space. I started with a vector space which is not finite dimensional. Okay. So, from this example we see that since I have started with that, then therefore, I indeed could achieve that the V mod W is not a vector space of finite dimension. So, this observation raises a very natural question that if instead I would have started with a finite dimensional vector space, then can it happen that the vector space V mod W is not finitely generated? I repeat, in the example I started with the infinite dimensional vector space and arrive at that this guy is not finite dimensional, and it seems that in that context in this context I was able to achieve that the quotient is not finite dimensional because I have started with a vector space which is not of finite dimension. It seems so apparently. So, that raises a very natural question that if I start with a finite dimensional, whether I can prove V mod W is finite dimensional or infinite dimensional. So, that we will be proving now. The answering that question is very easy. If we remember that the addition and multiplication, scalar multiplication V mod W are defined in this way. So, this shows that if V is finite dimensional, that is if I have a set, let us say V1 up to Vn which spans V, then if we look at the cosets V1 plus W up to Vn plus W, then very natural choice, let us call it S bar. So, now since any vector can be obtained as a linear combination of V1 V2 Vn, so therefore it is now clear that any coset in V mod W can be achieved as a linear combination of these cosets likewise. So, let me be more formal. So, if we start with a vector, so this is my verification. If we start with a vector in V, I know that there exist all scalars alpha I V I such that this is what happens. Okay, there exist scalars alpha I such that alpha V equal to alpha I summation alpha I V I, and then V plus W becomes alpha I. So, V plus W becomes alpha I V I plus W. Yeah. So, what we are doing is let us do it in 2 steps. So, the sum plus W, and we now know that sum plus W is W, it breaks in this way. Therefore, it now becomes alpha I V I plus W, and again the way it is defined we can simply regard it as alpha I times V I plus W. Okay, that shows if V1 V2 Vn is a generating set, then it's then the corresponding cosets here that generates V mod W. So, now we are quite convinced that we cannot achieve at a situation where V mod W is infinite dimensional if we start with a finite dimensional vector space, which is what I was talking about then, that I could have achieved in this context. I could have achieved that V mod W is not finite dimensional because I started with I could have achieved in this context that because I started with an infinite dimensional vector space, or well, by an infinite dimensional vector space I mean a vector space which is not finite dimensional. Okay, so that shows that if V is finitely generated, then V mod W is finitely generated. So, it is a very natural question to ask that given V is finitely generated, so we know that if a vector space is finitely generated, it always has a basis. Okay. So, starting with a finitely finitely generated, by that what I meant is it's finite dimensional. So, you ignore the word finitely generated. So, let me again come back. So, for a finite dimensional vector space we know that it has a basis. So, then for any subspace V mod W is also finite dimensional, then it is very natural to ask whether we can, whether like it is a finite dimensional vector space. So, it will have a basis, there is no doubt in that. The question is, can we have in a sense some can we have a basis which has which is somewhat I mean let me put it in this way. So, V is a finite dimensional vector space, so it has a basis. Being a subspace of V, W is a finite dimensional vector space, it has a basis. So, can we have, the question is whether we can have a basis of V mod W which has something to do with I mean well, I should make my question more precise. So, let us view, then let us go ahead, it will be clear. So, the question that I want to ask is, so given V is finite dimensional, V mod W will have a basis being finite dimensional. What I want to do right now is whether I can have a basis of V mod W such that, so let me frame the question in this way after several attempts. So, whether I can have a basis of V, a basis of W and a basis of V mod W such that these three bases are somewhat, these three bases are quite interconnected. So, so I have three vector spaces V W and V mod W. I want to get a base, whether I can make, I can frame form a basis or I can form a basis from each of these vector spaces which are in a sense connected. So, exactly that is what we will do here, and so V is a vector space of finite dimension. Being a subspace, W will have a finite, W will be finite dimensional. So, I assume that W1, so dimension let us assume dimension V is n and dimension W is m. So, m will always be less or equal to n. If m equal to n, then V mod W will have only coset W because V equal to W. So, in that case nothing to do. So, we can assume that m is less than n. So, okay. So, assume that is a basis of W. Okay. So, now if I look at the corresponding cosets of these Wi's, then all of them will correspond to W. So, W is nothing but the 0 element, the 0 vector in V mod W. So, these are not contributing anything in the basis of V mod W. Okay. They are not going to contribute anything, well, contribute anything other than the 0th element in the quotient space W. Now, what we do is we extend this basis to a UR let us say to a basis, extend to a basis of V, extend extend this to a basis of V, basis of V. So, these are my possibly extra elements. I repeat, the question that I was trying to frame there, that I have three vector spaces V W and V mod W. I want to get a basis from each one. So, therefore, I want to get three bases which are coherent in the sense that the bases are naturally interlinked. So, though the question is vague, but we will see what I mean within a moment or within a few moments. So, this is a basis of V mod W. Now, like all these elements, their cosets are nothing but W. So, they at the level of quotient space, all these contribute the 0 element. So, we can they are not of any use to us, but what about these vectors U1 to UR? So, we can consider U1 plus W plus UR plus W. Okay. So, this is a subset of V mod W. What is so interesting about this subset? Let us see that that and if you consider any vector in V, any vector V in V, then V, since this is the basis of V, so this is simply alpha I Wi plus let us say beta I, alpha beta I Ui. So, here I runs from 1 up to R, here I runs from 1 up to M. So, there exist scalars alpha i's and beta i's like this, and this implies V plus W, the coset. So, we started with the general vector V and I am looking at its coset. So, V plus W will be the coset of this plus the coset of this with the way we have defined the addition of two cosets. Okay. So, what will be the coset of this? So, this is a, so Wi's are in W, so this in W. So, since it is in W, its coset will be W itself. So, the first term will be W, and here as expected, so it will be beta times Ui plus W, right, or okay. Yeah, and this is nothing but, so since this can be regarded as 0 plus W, so we can add them. So, therefore, it clearly we can ignore this part, beta I times Ui plus W. Okay. I repeat, so the V plus W will be the coset of this plus the coset of this, coset of that. Okay. The so the coset of this is individually beta I Ui plus W, and their sum, that is same as individual cosets beta I W, beta I Ui plus W and their sum, and then you can further consider it as the multiplication of Ui plus W by the scalar beta I. So, what does that show? This shows you that beta I plus Vi. So, this U1 plus W, UR plus W, this is actually a subset of V which generates, this is a subset of V mod W which generates V mod W. Okay. And what about the linear independence? So, whenever there is a subset which is a generating set, we know that from that we can arrive at a basis. How do we do that? We look at this linear independence. If it is linearly independent, then we are done, otherwise we can reduce and reduce to arrive at a basis. So, whether this subset can work as a basis or not, we will check its linear independence. If so that means suppose that alpha I Ui plus W, where I runs from 1 up to n, if it is 0. So, what is 0 in the quotient space? The 0 vector is the W. So, the way it is defined again R, so alpha I Ui plus W, okay, and equal to W, and again the way if you remember the definition of two cosets, it will be simply alpha I Ui whole plus W equals to W R, which implies summation alpha I Ui I from 1 up to R is a member in W. A member in W means it has to be expressed by, it is to be expressed by this Wi's. So, that means there will exist gamma I Wi. Okay. Now, what you do is you bring everything on the left hand side, you get it 0, right. Yeah. So, there exists gamma I such that you get a linear combination of Ui's and Wi's, which is being which happens to be 0. From the linear independence, it forces that all the alpha i's, all alpha I and gamma j, all are 0, all ij. In particular, all alpha i's are 0, that shows this is a basis. So, we have seen that starting with a basis of W, if we extend that to a basis of V, then the extra elements that you have added here, the cosets of these elements will form a basis of V mod W, and as a corollary we see that, with that actually I will finish this lecture. So, what is the dimension of V mod W? So, given V is finite dimensional and having dimension m and dimension of W is m. So, what is dimension of V mod W? So, it becomes m plus r, oh sorry, it becomes r. So, r is the dimension of r is the dimension, yeah. So, so what is the dimension here of V mod W? It is r, and what is n, since this is a basis of V. So, this basis contains number of, what is the number of elements in this basis? M plus r. So, m plus r has to be n. So, r will be n minus m. So, we got dimension V minus dimension W. So, this is what the dimension of the quotient space V mod W. So, upshot is V mod W in general may not be finite dimensional, but if it is V is finite dimensional, then V mod W is also finite dimensional. Any generating set leads you to a generating set of V mod W, and starting with a basis of W, if you extend that to a basis of V, then this extra elements that you are adding here, their cosets will form a basis of V mod W there, and that gives you this dimension formula. Okay, with that I will stop this lecture. Thank you.